Hello, everyone. My name is XIE Zhiwei. We want to introduce the queuing management problems in banks and give you some additional thinking and suggestions to you. At present, due to the impact of the epidemic, banks in many countries and regions have begun to adopt the reservation system and work in parallel strategy to meet customers' needs to the greatest extent and improve customers' queuing experience. Walk-in customers will also be further split. For example, the Bank of China in Hong Kong will have two services after customers arrive, namely opening an account and general business, and self-service operated at ATMs. Now this paper focuses on the analysis of how the bank can optimize the queuing model in the case of customers having different needs with different service time, and the extent of self-service ticket machines will further optimize the queuing process. Conclusions are drawn by comparing MMN models. Firstly, an important variable of this model is the arrival rate of customers, which is denoted as lambda. The objective conditions that affect the arrival rate of customers may be as follows. First, the time is within weekdays or on Saturday. Second, customers' arrivals at different times of the day. Third, the impact of bad weather, for example, rainstorm or typhoon. Fourth, other unexpected events that cannot be predicted. Now, a rough analysis with conditional probability tree graph shows that the factors that determine the number of customers who are likely to visit the bank each day are roughly divided into two categories. Suppose a bank has about 40 or 400 potential customers every day, meaning they may travel to the bank that day with a probability of 0.3 bad weather and still choose to go, and a probability of 1 minus 0.3 good weather will go to the bank. At the same time, under the same conditions, there is a probability of 0.2 that customers still choose to go at the date of a specific event. Generally, such a date will lead to a sharp reduction of the windows for ordinary customers without an appointment. And on the contrary, there is a probability of 1 minus 0.2 that customers will not go to the bank on that day. That's the influence of each specific objective event on customers can be obtained. The weighted average tells us that on average there will be 157.7 number of customers would actually come to the bank every day. Since banks work an average of 9 hours a day, every minute there would be 0.3 customers coming, and the lambda would be 0.3.
My name is LIU Ziyin, and I will introduce the model building. Currently, the bank service system obeys two kinds of the forms. One is the queuing system, and the other one is the calling system. Queuing system is a traditional system which uses the theory of MM1 in Poisson distribution, and the calling approach seems similar to the queuing system but utilizes the different view MMN. Two models illustrate various results about some index. Queuing systems have some standard metrics. The leading performance indicators are 4. Other common quantitative indicators commonly used in the system are 6 indicators. Besides, both models have the same assumptions. First, there is no limit to the length of the queue. Second, customer arrival rate follows the Poisson distribution, and the service time per server obeys its proportional distribution. Third, customers have a random selection of the servers. Fourth, both systems obey the first come, first served principles, so that the waiting cost of each customer is in the same. What's more, the Markov model stands in an essential position in queuing model. Both the number calling system and the queue system utilize the Markov model. The first model is MM1. For the traditional queuing model MM1, each window only serves the customers in front of its window, and the customers cannot jump the queue at will. The traditional queuing system can be regarded as an MM1 queuing system, where customer arrival at the bank according to Poisson distribution. In the MM1 model, system utilization is less than 1. And in addition, MM1 model is an attractive object of a study which can be obtained from many metrics of the interest in this model. The other model is MMN. For this model, it shows that the bank has an end service and each server is independent. This model follows Poisson distribution either. However, the MMN model will not consider the file number case. The average service rate of the whole system should be mu. If the system utilization is less than 1, the system is smooth distribution.
My name is ZHUO Min, and I'm going to talk about the comparisons of MNE models and MN3 models. We calculated some of the important measures mentioned above to evaluate the waiting line model performance. In our study, we set n equal 3, lambda equal 0.3, and mu equal 0.4. The calculation results are as follows. From the measures calculated above, we found that the waiting line performance of the MN3 models is better than that of an MN1 models in terms of all the measures. On the one hand, the average time customers wait in line or spend in the MN3 model system is far less than that of the MN1 model, indicating that a great deal of customer time is saved by forming a single line for several windows, given the same service rates and customer arrival rates. On the other hand, the average numbers of customers waiting in line or the system is less when using MN3 models. This can largely avoid congestions in the bank, as a comfortable service environment can increase customer satisfaction to a great degree. Besides, when considering working efficiency, if a bank teller works 8 hours per day, under the MN3 models, the efficiency working hour for 3 tellers is about 22 hours. In comparison, the efficiency working hours for 3 tellers under 3 MN1 models is about 18 hours. Apparently, using a single shared queue can increase the service window utilization rate. From the above calculations and analysis, it can be concluded that the MN3 models has significant advantage over the MN1 models in this case regarding window idle probability, customer average waiting time, and other indicators. Another advantage of the single queuing multi-service DAX model is that this model considers fairness. Customers do not need to consider which queue to select as or customer queue in one line, which generously achieve first come, first served. Therefore, it is ensured that every customer is treated fairly. Currently, the calling system is frequently used in the bank. The customer selects the service categories he needs and obtains a ticket from the ticket printer. The basic information on the receipt is the queuing numbers, estimated waiting time, the numbers of people waiting, the waiting areas, and other information that can be displayed as required. The bank used the window display board for calling queuing numbers. The main display is placed in the prominent position in the waiting areas for all waiting customers to see. When a new customer number is called, the customer and the service counter numbers will be displayed along with the voice prompts. As a result, customers don't have to stand in line and just sit to wait. This is superior to the traditional queuing system, which reduces customer waiting time. This is the practical applications of the MN3 models, which changed the queuing system from the past multi-queue to single service desk model to the single queue multi-service desk model.
Okay, my name is PEI Yumeng, and then let me introduce the suggestion. After analyzing and comparing the two models of MMN and NMN1 above, we know that the former has considerable benefits over the latter. So we can also put forward some focused suggestions to enhance the queuing system. The first one is to establish a flexible numbering scheme for service windows. At different times of the day, the number of service windows may be adjusted freely. When the customer flow is low, for example, the opening of the windows might be decreased. To reduce the customer waiting time when the queue is big, all the windows must be opened. And second, it can be used in combination with queuing and calling. When the customer flow is quite big, both queuing and calling system may be utilized to increase the customer satisfaction. When the customer flow is relatively small, only the queuing system can be used to improve the efficiency. And then, during the time while customers are waiting for service, the service staff can complete some auxiliary work for customers, such as the customer's idle time should be efficiently utilized by the bank. For example, the employees can question each customer about their business needs, help them through the process of filling out documentation ahead of time, and so on. They can also post the promotional materials and display advertisement on the display screen in the restroom to promote their own business. Furthermore, this approach can create an improved customer experience, as customers may feel that their time is being respected and valued. The last and the most important one is to segment the customers. Different customers need to handle different businesses. For example, most customers need to handle routine business, such as the deposit, withdrawal, and so on. There are also some urgent or auxiliary businesses, such as the currency exchange or payment. The bank can set up different service counters to improve the service efficiency. At the same time, the VIP rooms can also be set up to receive the big customers and make them feel at home. And next, we need to use the simulation model to analyze whether providing different types of service through different windows will affect the overall service of the bank. Let's welcome my partner.
Thanks. My name is CHEN Yankun. First, I would like to introduce the construction of the simulation model. In a bank counter service, suppose the service can be divided into two categories. One is for the general depositors, including deposit, withdrawal, and transfer businesses, and the other is for other customers, including payment business, etc. We call the latter ones type 1 customer and the general depositors as type 2 customer. All the counters can serve the general depositors, while the service for type 1 customers is restricted to the designated counter. Assume that half of the counters in the bank can serve type 1 and type 2 customers can be served at all counters. Therefore, it can be considered that there are two service counters in the system in parallel as counter A and B respectively. The arrival rates of type 1 and type 2 customers are lambda 1 and lambda 2 respectively, where type 1 is restricted to be served only at counter A. The service rate of counter A and counter B is mu1 and mu2 and satisfy the condition of rho equals lambda divided by mu. Then, according to the previous finding, MM1 is more efficient, so we suppose that there is only one queue in the system, and customers enter the queue in turn with no priority, which means when counter A is in service, type 1 customers can only enter it if the customer in front of him is finished his service. But if counter B is free, and there is a type 2 customer in the queue, then this kind of customer can pass the type 1 customer in front of him and enter counter B directly. Let the system state be x1, x2, x3, where xi is the number of type I customer. When type 1 customer is receiving service, x3 equals 1, otherwise it is 0. P represents the probability that the system state is x1, x2, x3. According to the above two theorems about the service rate and the intensity coefficient of letter elements entering the counter, the state transfer diagram of the system can be shown below. It should be noted that if there is only one type 2 customer in the system, he should be served at counter B. If the service for him has not been completed at counter A, then he will immediately be transferred to counter B to continue his service, and it has no losses. Therefore, we calculate the possibilities described by the following equations and let Q be the sum. Since Ix equals P00, so mark I0 equals I0x, then it can be obtained that when both two counters are providing services, F11 is row 1, while I11 is 1 minus row 1. Therefore, the probability of having one type of customer being served in the system is only related to the customer arrival rate and service rate. Thus, using half of the counters for type 1 customers will not impact the services for the majority type 2 customers. Now, welcome my partner to talk more about the application of this model.
Okay, my name is Haijie.
请稍后。
Now let me introduce my part. First is the
人在处理。
application of queuing model in order to ensure the optimal design with the minimum total cost. We try to construct a cost structure based on the actual situation. We assume that the system has two types of costs. One is waiting cost. So the waiting cost per customer per unit time of stay in the system is C. And the other is service cost. The cost per survey task per unit time spent is A. And so we can come up with this formula. And in this formula, Q bar is the average number of customers in the system. So with this equation for the average total cost, the optimal value N for minimizing the average total cost can be determined. And next is simulation rounds of the model. We established numerical simulation of the model by the one-round method, and based on the information above, we can get these results. That is, the probability that the first type of customers is served in this model is 0.97, so the chance of being served is very high. And we let the number of the first and second type of customers waiting for it in the system when the unserved customer leaves be LN1 and LN2 respectively. And the total number of customers waiting in the system be LN when the unserved customer leaves. The average waiting captain of the first and second type of customers in the system is L1 and L2 respectively, and the average waiting captain of the system as a whole is L. And finally, we have these results. And we can see that W is between W1 and W2. In fact, although this queuing model increases the waiting time of the first type of customers in the system, it also increases the chance of the second type of customers to be served. Therefore, it is necessary to make some economic evaluation of this system. So we let the waiting cost per unit time of the first and second type of customer in the system to be C1 and C2. And the cost spent by each service task in the unit time is still A. So the total cost of the system in the unit time is M equals to 7.6 C1 plus 9.76 C2 plus 2A. And finally is the practical implications. From the above analysis, it can be seen that in the counter service of banks using queuing machines, if customers who are allowed to conduct general business can be served at all windows, then half of the windows can be opened for customers who are not doing general business without affecting the overall service of the bank. And this system is mutually beneficial to the customer and the management. The new queuing concept applied in real life will greatly improve the service quality of the corporate window and establish a good corporate image. And that's all for our presentation. Thanks for listening.